So, welcome back, class 2. You made it through class 1. Yay. So, today's class is going to be on computers and their business applications. I have to admit, I think this chapter or module, I think is how they call it, is like one of my favorite, being a computer science professor. So I may geek out, and I apologize, but not really, because I like geeking out, so it's fine. Um, so this is just a basic understanding of computers. We're going to look into the computer system as a whole. We're going to look at some backstory and some back history, which is very, very interesting. We're going to look at some basic operations. We're going to actually pick apart what some of the pieces are, because as you go into business, you want to be able to hold those conversations with the rest of your departments and understand what they're saying. You don't want them to be completely speaking a different language. So there are some basic pieces of a computer that usually come up in general conversation when you're looking at business. So we're going to go over some of those. We're going to go over some computing classifications. We're going to talk about some software and hardware and what the differences are. And then we're going to wrap up a little bit with different programming languages and object-oriented programming. So let's go ahead and get started. So when we define a computer is a machine. Okay, this machine is going to accept data as input. It's going to do something and process it without human intervention. Okay, it does this by accessing a group of stored instructions that is what we call the program or the software. Then it is going to output the information. So remember, last class, we discussed about how we have to gather the data and store the data and then process it. And then we have an output of some kind of report. That's basically what a computer does, but without that human intervention element. Okay, computers cannot think for themselves. They need instructions. So in order to give them instructions, what you do is you give it a computer program. These programs can be in various different languages, and they can be at different levels, and we'll talk about that in a little bit. The biggest thing that we have to understand with computers is that, I love this phrase, garbage in, garbage out. Your computer is not going to be smart enough to know that the data that it has is not useful. So if you give it, data that is unusable, it's going to spit out reports that are unusable. So, unless you built in to the program some kind of cleaning up method, whatever you give the computer, that's what it's going to process, and that is what it's going to output. So if it is incorrect, everything's going to be incorrect. Okay, so that's something to kind of remember about a computer. Now, a computer needs instructions, like we say up here. These instructions are going to identify what has to be done. Okay, what you have to do is you're going to have to plan out a procedure. Okay, when you do the planning of the procedure, it includes logic, it includes selecting the proper language, it includes selecting the proper hardware that's necessary. This is where you get into the computer science realm, which is where I live, okay? We're the people that write these instructions, okay? These instructions always depend upon the problem being solved and what computer you're using, okay? If you're using a Mac, it might be an app. If you're using a smartphone, it might be an app. If you're using a PC, it might be a whole blown out program, okay? These instructions, what we call them is source code. So source code is going to have to be translated into object code, okay? Basically, what we're doing with source code is we're taking it in English and doing a translation into computer. Computer can only speak one language, let's say it that way, and it can only say two things, okay? A computer is an electronic piece of equipment. Therefore, it's either on or it's off, okay? That's all it can do. That's all it knows is on and off. That means that it has two different settings, right? Basically, we call these a 0 and a 1. For off, 0 is off, 1 is on. We call this binary. Bi because there are two different options, and binary comprises that numbering system, okay? It's going to translate these zeros and ones into these on-off signals. Okay, remember, it's a piece of electronic. All it knows is on and off. It's basically just like a light switch. So hardware versus software, we're going to go ahead and we're going to start with hardware, but hardware is your physical devices. It's what you can touch. It's what you can see. It is what you can feel, okay? It's your physical devices, such as your keyboards, monitors, mice, things like that, your processing units, your actual box that you have. Software, on the other hand, are going to be those things that are these programs of instructions within the computer, written in different computer languages, okay? So the easiest way to remember that is hardware is hard, you can touch it. Software, there's nothing to touch, you can't feel it. Okay, so that's the difference between hardware and software. Let's go ahead, let's start with hardware. We're going to go through a few different pieces. So the first piece I have here, and there's a picture of it here, is what is called a CPU. If you've heard that before, it is a central processing unit. This is kind of like the little brain of your computer. This is going to have a few different pieces. There is an arithmetic logic unit, or an ALU, and a control unit. The ALU is going to be in charge of, just like it sounds, all the arithmetic, okay? It's going to be your plus or minus, add, subtract, same thing, multiply, divide, okay? And your comparison, your comparison operators, is this greater than or equal to, is this equal to this, things like that. The control unit, on the other hand, that's going to tell the computer what to do, such as telling the computer which device to send the output to. I have multiple monitors at my setup at home. Actually, I do at work too, in my office. I have multiple monitors. So that control unit says, okay, for this, I want to display this on monitor 1, this on monitor 2, and this on monitor 3. So it's going to know what to do with the different pieces of hardware. Computers have what is called a processor, and this is going to just do like it sounds. It's going to do the processing. Computers can either have a single processor, or it is called a multiprocessor. So it's either one or more than one, is basically how it's described in the computer system. Multiprocessing is going to be two or more of these CPUs in a single system, okay? So a single processor is one CPU, multiprocessor, remember, more than one, but we're talking about CPUs when we're looking at this processing. Next is something called a bus. Now, a bus is just a fancy word for a wire. I'm just going to say it. It's a fancy word for a wire. In the, dictionary definition, it is the link between devices within the computer. Okay, there are many different types of bus. It was given the term bus because if you think about it, a bus just basically takes people from point A to point B. A bus is just a link. Okay, there are different kinds of buses. There are internal and external. External, you probably see. This technically, oops, I just attached to my shirt. This technically is a bus. This bus is taking the information from my headphones into the box that is on the floor, because it's huge and I don't have that much desk room. But technically that is an external bus. That is something that I can, touch and I can plug in and out. Internal bus, typically there are those larger, fatter, flat ribbon cables that you'll see. I was trying to grab one before I started class because I've got a bone computer back here. And if you don't know what a bone computer is, it's just kind of a computer that's used for parts. And I couldn't find a nice internal bus example that I wanted, but those are the things that are connecting like your hard drives to your motherboard. You're connecting the audio and video inputs into other places on the motherboard. So those are all called bus. There are two sort of main types that we talk about as a parallel or a serial. And that just has to do with how that bus transfers the information. It can either transfer two-way in parallel, like one way going in, one way going out, and that's a parallel, or it can do it in serial, which means it can only do input and or output at one time. It can't do both at the same time. That's all that that means. Let's move on to a disk drive. So this is a peripheral device used for recording, storing, and retrieving. I do have one of these. For recording information. And the only reason why I have this is because my disk drive died like last week, and I had to use the one out of the boneyard over here to get my computer to boot up. So this is what a hard drive would look like. Now, this is an internal hard drive. This would be inside the box that you have in the computer. And this is what is going to be your storage on the inside. There's not a whole lot to look at. I really kind of want to try to take this apart a little bit more, but not a whole lot to look at. Other kinds of drives, you've got CD drives that are in some, I don't even think mine has a CD drive, but you've got CD drives, but basically it's just any kind of device used for storing information, internal and or external. You can have an external bus, you've got external hard drives, which may, again, these are not cute, okay? It just looks like mine's just a little black box. This is my external hard drive, and it stores information. You also have things like thumb drives, which I don't think I have any of those either. Thumb drives or SD cards, these are all kind of in that same realm of disk drive. We have something called a CPU and motherboard. So the CPU case is basically the outside box that holds everything in it together. It's going to hold all those components in and keep them safe. We are dealing with electronics, and a lot of them are fragile. So, you know, mine is under my desk. If I were to kick it, say, like I do probably 30 times a day, if I did not have a robust case on it, I could break some of those connections. Okay, sometimes you hear it referred to as a chassis. There's also a version called a tower, which is a more of an upright configuration. What I have is considered a tower. There are also the ones that are more horizontal than vertical, that are more like considered desktop as opposed to tower. Within that case, there is a huge circuit board. This circuit board is called the motherboard. It basically has all of the connections for everything, okay? It will connect your CPU to the input output system, to the memory, to the storage. It has the ability for expansion. Okay, this is a picture right here of what a motherboard looks like. Typically, your CPU is sitting on there in some location. You know, again, you've got basic input output systems, or BIOS. If you've ever heard the word BIOS, it stands for basic input output system. Again, computers, we love our acronyms. There's places for the memory to be linked into. And that's where you would add memory chips in order to expand your memory. So that kind of wraps up all the information in a computer system and talking about the hardware. So let's look a little bit at the history of computer hardware and software. So major developments have taken place over the past, you know, I think the book says 60 years, but, you know, it's probably since the 70s and 80s. Those of us that were alive during that, not to date myself, um, we kind of had a really cool experience experiencing most of this going on. In order to make a clean break through the history, they decided to break up things that were going on into what they called generations. So there's first, second, third, fourth, and fifth generation. We'll go through each one of these so that you can understand what happened in that generation. So let's look at first generation first. Now this is pre-1970s. So we're talking about in the like 40s and 50s. They had things in using vacuum tubes and it was called an ENAC system. You can see so this picture right here is the person working right there is replacing a bad tube in an ENAC. Now, this whole picture is one computer. This whole picture is probably not all of that one computer. Okay, so this was definitely not portable. This was definitely meant for businesses and organizations that needed that computing power. Let's go ahead and let's click on second generation and let's see what that looks like. So second generation, now we're talking late 50s into the early 60s. This is when it really kind of started to ramp up. We went from those vacuum tubes into transistors, and IBM was one of the first to implement their versions of these second generation computers. These are pictures right here of the IBM 7094 and 1401. What you can see, the very first picture, the one right here, this whole thing is a computer. These are not bits and pieces of the computer. All these boxes working together is the computer. The same thing with the second picture. Okay, again, we're not portable. We're not very user-friendly. I don't even say we're not very user-friendly. We are not user-friendly. How's that? Was that better? You had to be very specialized and know what was going on. Let's go back to our main screen. Let's go ahead and we're going to click on third generation. So the third generation, this is really when things started to launch. We're talking 60s to 70s, integrated circuits, remote data entry, and telecommunications. Again, we have IBM as one of the people in the forefront of this whole industry. They came up with an IBM 360 and a 370. Again, you can see from both these pictures, not much has changed between second generation and third generation as far as physical hardware and looks. What has changed is what is in the inside and in the guts of the computer. Okay, so we are still, this picture right here, this picture right there is still a very large computer. Okay, so that has not changed at all. Let's go on down to the fourth generation. Now, this is the 70s through the 90s. This is sort of where I grew up, in this whole array. This is miniaturization via VSLI, PCs, optical discs. We're really starting to get smaller and much more advanced when we're talking about computers. Okay, we're starting to get them to be portable. We're starting to get them to have, laptops and things of that nature. Last but not least, we have fifth generation, which is kind of early 90s to now. We've got parallel processing, where we've got multiprocessors in our machines to make them faster, lighter, stronger. We've got optical technologies, and we've got much more advanced materials being used in our chips. This is an example here of an IBM Z system enterprise. It's still quite large, but the computing power of this compared to some of those earlier ones is completely different. So that goes through a little bit of just a quick synopsis of the different generations of computers. The biggest thing is to remember is like a vacuum tube. We started getting a little bit more into transistors. And then, as we're evolving, fourth generation is really making a personal PC a thing as opposed to, what they had previously. Let's go on to the three factors of the power of computers. So computers draw their power from three things that far exceed any human capacity, right? Speed, accuracy, and your storage and retrieval capabilities. Those of us that are older, my storage and retrieval capabilities are terrible. I'm just saying. I've got lots of notes and lots of notebooks. So a computer far exceeds me on that one. Some of your younger folk, maybe not so much. But the whole draw to a computer is that it is faster, it is more accurate, it will not make mistakes, except for the garbage in, garbage out, because that's not technically a mistake, okay? If you give it the correct input, it will do the process and give you the correct output every single time. There's no math mistakes. There's no translating from handwriting or, transposing numbers. The accuracy is tip top. And then last is the storage and retrieval capabilities. So speed, computer speed is measured as the number of instructions performed per a fraction of a second, okay? We're talking milliseconds, microseconds, nanoseconds, picoseconds, okay? A millisecond is 1/1000th of a second. I don't even think I could put a thought together in that short amount of time, right? This speed is way beyond anything that I have in my own capabilities. Okay, so remember, we're talking fractions of seconds. The degree of accuracy that a computer can give you is crucial, right? In many of your applications. Otherwise, why would we want to rely on a computers if it's just going to make mistakes? A small degree of inaccuracy, it could lead to the space shuttle landing in Canada instead of United States, right? There are small little things that errors can basically accentuate, okay? Computers have the ability to not have those errors, so those are things that are not worried about when you're using these machines. Storage, again, this is saving that data in computer memory or on hard drives when it works, because like I said, mine just died. Retrieval is accessing that memory. That's, I think, what I have problems with my old lady brain, okay, is accessing the data from my memory. Data is stored in bits, okay, and then the bits come back into that binary code and a byte. So the American Standard Code for Information Interchange, if anyone has heard of ASCII code, that is what ASCII stands for. It stands for American Standard Code for Information Interchange. It is code for text files, PC applications, and the internet. They really were the first one to put a method and a process out there that spanned, languages, and it spanned different operating systems. It defines up to 128 characters. So when we look at our alphabet, we've got uppercase and lowercase. So that's what, like 48 or something like that? No, 52. But there's additional characters that we want to have access to, right? Yeah, my math brain, I'm telling you. I'm looking at my keyboard. There's periods and commas and semicolons and colons and additions and ampersands and percentages. All of these, we had to come up with a common way to indicate that that is what I'm talking about. That's where ASCII code comes in. An ampersand in ASCII is going to be the same whether you're on a PC, a Mac, whether you're using Java or BASIC, it's always going to be the same. So it's a standardization of your characters that you're wanting to see. I'm going to go ahead and click my face off because otherwise there's going to be a table in my face. Here are some quick storage measurements. So you hear these things again as you talk amongst your business professionals. So a bit is a single value, which is a single 0 or a 1. We talked about that binary. So a single switch we can think of as a bit. Okay, so it's going to be a 0 or a 1. 8 of these bits is called a byte. So a grouping of 8 of these is what is a byte. 1,000 of them, or 2 to the 10. Okay, one thing you're going to notice is that these storage measurements are numeric values that are of base 2. Okay, so you're going to increase sort of exponentially. Okay, so 8 is actually 2 to the 4, right? No, 2 times 2 times 2 times 2. No, it is a 2 times 2. It's 4 times 2. It's 3. Okay, times 2. Yeah, got it. So 2 to the 10 is going to be 1,000, and that's what's going to jump you from a byte to a kilobyte. Okay, 2 to the 20 is going to be, let's see, 1,000, a million, and it's going to be a megabyte. And then 2 to the 30 bytes is going to be your gigabyte. So you can see these are going to increase exponentially by just adding 1 bit on either side. Okay, so that goes into those 3 factors that make a computer much more lucrative than the human brain. Let's look at some basic operations. So some basic computer functions, sorry, are arithmetic, which is math, logical operations, which is basically your comparison, and your storage and retrieval. Those are the 3 basic tasks that your computer can do. Everything is a mixture of those things, okay? So your arithmetic operations, just your add, your subtract, your multiply, divide, raising to exponents, you know, doing calculations of any kind and of any sort. Logical operations are your comparison. You're going to compare 2 values, whether you're comparing a variable value to a hard number value, or you're comparing multiple variable values. I need more coffee. These late nights. Anyway, the last thing it can do is an input output, which is a storage and retrieval. So we look at input as a retrieval and output as a storage. Okay, so it is able to store massive amounts of data in very, very small spaces. So this drive right here is a terabyte. And this one, look at that, that's a terabyte too. These are both a terabyte. These are very, very small. But again, this one's much smaller than that one, but they hold the same amount. Okay. And it is, my computer is able to access the information on either one of those very, very fast. So basically, when we think about it, your computer can only do 3 different things. Remember, math, comparison, input, output, or storage and retrieval. Let's go back to our main screen here. And the next one we've got is devices. So when we look at devices, we're going to look at 3 different things. 3 components are needed in order to have a computer successfully do anything, okay? Input, output, and memory. Let's look at input devices first. So input devices, this is going to send your data and your information to the computer. Input devices, we can talk as far as, keyboards. I guess I should stop saying the back of the keyboard because it doesn't even look like a keyboard. Keyboards, mice, stylus, trackball, because I've even got like this little tablet that you write on and it shows up on the screen. Any kind of character reader, an optical, optical mark recognition or OMR system. Even my microphone is an input. My headphones are actually an input output, and we'll talk about that one in just a second. So let's go on out to output devices. So my output portion of my headphones is the actual headphone portion, and the input is the microphone. So it's actually both an input and an output. There are many different devices available for output for both mainframes and personal computers. There are 2 different types of display. We call them a hard version or a soft version. So a soft copy would be something, again, not tangible. Remember, software, soft copy. A hard copy would be something that you can hold in your hand and take with you, like something printed on a piece of paper. Other types of output devices, your screens, your CRT, LCD, whatever type of screen that you have, your printer, those are the most obvious. There are some other ones like plotters, voice synthesizers, speakers are a good version of output. So when you're looking at a program, you want to be able to take information and then display it back, which really goes along with all the stuff that we were talking about yesterday when we were looking at the different methods. Last but not least, let's go ahead and select the memory devices. There are 2 different types of memory devices. There is main memory and there is secondary memory. The main memory, let's do that one first. It's going to store data and information that we call volatile. What that means, volatile information is basically gone once your electrical power is is turned off, okay? They are semiconductor chips made from silicone. It could be either volatile or non-volatile. Some of the main different types that you may have heard of is RAM. RAM is random access memory. It is volatile. It is read-write memory and it sits on the processor. Okay, remember your RAM is volatile, which means as soon as you turn your computer off, whatever was being held in there is gone forever. The second type that we have here is called ROM. So it is read-only memory. It is non-volatile, which means that it never goes away. Now, the difference with this being in main memory is that data cannot be written to it. Okay, what's going to be on your read-only memory, because it's read-only, right? So you can't write to it. What's going to be on your read-only memory are typically your BIOS information, things like your system clock, how to start up your computer, how to start up your iOS, or no, your operating system, that one. Okay, these are the things that are going to be on that ROM. It's not just a typical, memory that's accessed, and we don't just write to it like we would read, regular memory. So what are some other types of ROM that, nope, I lied. What are some other types of main memory maybe that y'all can think about? Some of them are things called a PROM, which is a programmable read-only. And then there's something called an EPROM, which is an erasable programmable read-only. Again, we love our acronyms. So that's about all there is for main memory. We can go ahead, let's go ahead and click on secondary memory. Now, secondary memory is going to be things that you're used to seeing and being able to, touch and see and take advantage of. Typically, these are all non-volatile. They're used for storing large amounts of data for large amounts of time. So, this is something that we want to keep beyond shutting that computer down, okay? Over however many, we want to specify when we want this to be deleted and not have the computer do it for us. Things like magnetic disks, that's what's going to be in, if I was able to take this off, they're made of mylar or metal used for random access processing. There are things called magnetic tape. Again, it's made from a plastic material. It stores data sequentially. Sequential storage is usually faster than random storage. So that is what gives magnetic tape a little bit of a leg up on top of a disk. Other devices, hard drives, USB flash drives, memory cards, SSD. That's the newest kind of version. Is my SSD? Yeah, it is. So this is what an SSD is. This is actually a hard drive. This is also a terabyte. The difference is SSD is a solid state drive, which basically means it has no moving parts in it. Okay, it is just read electronically, whereas this, I wish I could have taken that off, whereas this actually has things that spin, things that read it. It looks more like that picture right there. Let's look at what something called a RAID. A RAID is going to be a redundant array of independent disks. So what it is it's a collection of disk drives used for improved performance. It is used for fault tolerances, so it is making your information much more secure. These are typically found in much larger networking systems. So if you have a shared drive at, where your place of employment, things like that. Now let's go back and look at that last one, because that last one right there has been kind of the one that's been the buzzword lately, right? We've got cloud storage. Cloud storage is all online. It involves multiple virtual servers. They're all hosted by third parties. You can access your data anytime, anywhere. Okay. It is improved security. You have better collaboration. I was able to share with you the template for the um, the case study virtually, and you were able to grab that. And because it's stored out there on a cloud drive, I put it out there on my Google Drive for everyone. So we're moving a lot towards cloud storage, especially with just having various locations to co-locations for working, school, things of that nature. I tend to put my programs on my local machines, but I do tend to keep my data out on a cloud drive that I use. That way, I'm able to access it from my work laptop, my home laptop, or my desktop setup, and sometimes even my tablets. So that's always been sort of a draw for that cloud system that's out there. So those are the two different types of memory that we have, and that pretty much finishes up the input, output, and memory devices. So let's take a quick look back over here, and let's look at the classifications next. So we're going to classify our computers based on cost, how much memory they have, their speed, and how sophisticated they are. A lot of it is based on size as well. We're going to look at 5 different ones here. We've got a notebook or a sub notebook. We've got a personal mini computer. We've got a mainframe. We've got a super computer, and we've got a server. So let's look at the server platforms first. Server platform. These are going to be your application servers. These computers and all the software for managing your network resources and offering these services through your network. Okay, these are your central locations. You can have things that are servers that are application specific, or you can just have a storage server. So you can have servers that just run applications, that just run websites, that just run email. So if you have a Gmail account, Gmail has a mail server. Okay, and all of the mail that goes in and out of Gmail goes to that mail server. You can have database, disk, fax, file servers. Typically the file servers are what you have in your employment and or at the university. You can also have print servers, which is what we're implementing right now at CU. You can print to one location and then get it from anywhere. You have remote access servers, and like I said, you have some web servers in there. So let's go back. Let's go up to supercomputer. So what is a supercomputer? A supercomputer is the fastest computer currently available. Okay, they're typically used for simulations in exploration and production of various industries such as, petroleum, natural gas. It can be used for structural analysis, computational fluid dynamics, physics, chemistry, design, nuclear energy research, meteorology. These are things that are going to require the computing power of something as large as a supercomputer. Next, let's take a quick look at a mainframe. A mainframe is the traditional large institutional computer intended to serve multiple user from the smaller single user machines. Okay, these are going to be the computers capable of handling and processing very large amounts of data very, very quickly. Mainframe computers are used in large institutions such as governments, banks, large corporations. Basically, it is the entire structure that includes your PCs with some kind of hub, and then you've got some terminals with some processing. These are going to be the large computers that are going to be that will occupy an entire room. Let's go up to personal mini computer. This is your traditional desktop or laptop. This is what we see on a daily basis is what's considered a personal mini computer. It has a screen and a keyboard and a mouse. It's a single user computer. It is all self-contained. You don't need to be connected to the internet. You don't need to be connected to any other type of device in order for that computer to do what it needs to do. Finally, we've got this stub notebook and notebook. This is going to be a very small laptop computer. Typically, we say it weighs under 4 pounds. In order to reduce the weight, sometimes they're called ultra books or ultra lights. Um, Typically, they do not have, CDs or DVD drives. There's not a lot of ports on them for peripherals. These are the ones that a lot of times are found in trucks or police cars or things like that. They have very small screens, 8 to 10 inches only, as opposed to, I mean, now I think laptop screens are up to 15, 17 inches. Oh, Nick's here. 15, 17 inches. So you can see the difference in the screen size when you're talking about this sub notebook. Okay, let's go into the computer software. So, the programs that run a computer system, that's going to be your software. The system software and is application software, two different types of software, two different classifications. Your system software is going to be your operating system. That's what's going to run in the background and take care of much of the tasks of just the everyday life, okay? It's going to allow you to move files and delete files and just start up your screen, show you your desktop. It's going to be those basic operations. Now, application software, on the other hand, it is going to be a very specific specialized task. Zoom is an application software. It is video conferencing. That is all it does. That is all it knows. That is its life, right? As opposed to the operating system being Windows, iOS, things of that nature, where it just kind of runs in the background and these applications will run on top of them. Let's take a quick look a little bit closer at application software. So this is going to perform a task. Some examples: word processing, spreadsheets, CAD. What other types of application software can you guys think of? Anything good? Graphics, desktop publishing, um, you know, database, things of that nature. Okay, these are very, very specific applications that do a very specific thing. Let's look at this operating system software on the other hand. This is going to provide a user interface between the computer and your user. Okay, so it's going to kind of be your go-between. It increases the computer efficiency by helping your user share the resources and performing repetitive tasks. Okay. What are some tasks that the operating system software could do? So it can do job management, it can do resource allocation, it can do data management, it can do communication. It is responsible for controlling all of the other programs in the operating system. Okay. It is going to supervise and make sure everybody's running properly and everybody's happy. So that in a nutshell is what your operating system software is. Let's go ahead and head back to our main screen. We've got two more topics to cover. Let's go ahead and jump into computer languages. This is one of my favorite. I love my computer languages. Um, so we're going to look at different types of languages that are out there. We have things like machine language, assembly language, high level. Then we have a 4G, a fourth generation, and a fifth generation language. So let's look at machine language first. And as you can see, actually in this picture that's here, they're kind of different varying levels of languages. So let's start at the top. Let's go to machine language first. Machine language is considered a first generation. Okay, this is speaking in that binary code. You are going to have ones and zeros. They're going to be everywhere. That's how you're going to tell the computer what to do. It is very dependent from machine to machine. And when I say machine to machine, I'm not talking Windows versus Apple. I'm talking about Intel versus IBM versus Dell, whatever manufacturer that you have of your computer. So it is very, very time consuming to write a program in machine language. Machine language is going to have to be rewritten on every single manufacturer, no matter who you want to run it. Here's an example of it. It's just ugly. Like it's just ugly. But just remember, machine language is what your computer speaks. Second generation, let's go to assembly language. And I covered my face a little bit, and that's okay. Assembly language is a second generation. It is one step up from your machine language, but we are also still machine dependent here. Okay, it's going to use a series of short codes or mnemonics to represent the instructions, and so it's easier to write than machine language because we're starting to transgress into English, but that's still ugly and kind of very time consuming and difficult to read. Now, high level is where we start getting into things that are better understood by humans. Okay, this is the third generation of computer languages. Again, this is machine dependent, but at this point, we're talking more operating system dependent than hardware dependent. Okay, so it's machine independent. Used for web developments and internet, that was a weird accent on there. Internet applications. That's why you can run a website on a Mac or a PC or things like that. A lot of them are self-documenting and that easier to learn to code. What are some high-level languages that you can think of? How about languages such as Fortran, COBOL, BASIC, Java, C, C++? These are all your high-level languages. Take a quick look at these fourth generation languages. So fourth generation languages are your object-oriented languages. Now we are going to be talking a little bit more about specifically object-oriented, but again, we're moving closer and closer to the way that humans think, speak, and conceptualize, okay? A lot of fourth generation languages are associated with databases such as SQL. SQL is a fourth generation language. It is easy to learn. It's applicable for any database. So anyone that knows SQL, this is an example of what an SQL looks like. Select name average from results where average is greater than 75. You don't need a whole lot of computer programming knowledge to kind of understand what they're looking for here. What they're doing is they're selecting the name and the average from the table called results, anyone whose average is bigger than 75. So basically anyone that has passed the class, okay? You can just look at that and kind of know what's going on. It's using those macro codes that can take the place of several different lines of programming. Let's quick jump back and let's look at this last one, this fifth generation. And you can totally not see me in this one, so I'm just going to go this way. Haha. Okay, so your fifth generation programming languages. This is a group of programming languages built on the premise that a problem can be solved and an application built to solve it by telling the computer constraints rather than telling the computer how to do it. Now we are dipping our toes into AI, okay, and your artificial intelligence. Artificial intelligence, all that is meaning that your computer will make the decisions if you tell it the constraints and you tell it what you want it to do, as opposed to telling it how to do it. The example shown here is a language called Mercury, and that is giving it constraints, and the computer is going to do a little bit more quote unquote thinking. Okay, it's a knowledge-based system, it's natural language processing, visual programming, graphical approaches to programming. Okay, so we're taking the programming and really giving it to the masses. It's designed to facilitate natural conversation between the individual and the computer. This is like Alexa, okay? So you speak, oh, I just want to make sure I didn't turn her on. I need to change her name up here in my office. So you talk to her and you tell her what you want, and then she is able to do something based on that. Okay, so that's where we're heading with these languages, is that they're getting to be quote unquote smarter and to be able to think for themselves. But basically, really what you're doing is you're building in the ability for it to learn and go through these neural networks. Really, the biggest thing to take away from this whole section that is computer languages is that there is a range of them where machine language is first generation and it is basically speaking in binary ones and zeros. You've got assembly and then high level and then 4G. Most programmers sit in this third generation level, and that's where your Python and Java and JavaScript and things like that are going to kind of sit in that section. Okay, let's go back to this main screen. Our last topic for today is our object-oriented programming. So let me click on that one. So this is the next step in programming, like we had talked about. It is organized around a system that are called objects. Okay, these objects are going to represent the real world as opposed to a series of steps used in traditional languages. So there are two main parts to it. There is an object and a class. So your object is basically nouns and it is your thing. Your classes are going to be your verbs and it's going to do something. So first, let's look at objects. The object is going to be self-contained. And what it's going to contain is it's going to contain the data and the procedures. So it knows what to do and how to do what it needs to do. So I can say I have an object that is a car. We've got cars. What do cars do? Okay, cars drive, cars get you from A to B, cars take gasoline, and cars turn on when you put the key in. Easy peasy, right? Now I can create an object that is of a type car. Okay, I can create a minivan. A minivan is a car. Okay, it knows how to do what it needs to do. The very abstract kind of concept. When you start applying this, though, it really makes sense. It makes things much more portable, and we'll look at some of the other advantages of it. But basically, it is self-contained. It knows its own procedures and it has its all own information. Now, let's go back and let's talk about the difference between the classes. So the class is going to define the format of the object and the action to perform it. So the class is that car part. What is a car going to do? What is a car going to have? How is a car going to operate? Those are the things that the classes is going to have. The class will have that it will give to each of the objects. Okay, so your Beetle has a windshield, it has a trunk, and it has an engine. Okay, so does your Mini, and so does your Polo. That's kind of what we're talking about when we're talking about these objects in object-oriented programming. Some advantages of object-oriented programming. The biggest one is modularity and reusability. It is written for a specific purpose and it is self-contained. They're easier to write, modify, and troubleshoot versus traditional code because it is self-contained. Okay, once you've also done all the error checking and you've got it working properly, you can use it as many times as you want. Okay, so you can reuse that code for as many different purposes as you would like. If you want to add new features or new modules without impacting anything else, if you write it within that class, anything that uses that class will have those new features. Okay, so your codes can be written for one object and they can be very easily modified for another object, sorry. It has effective problem solving. You could break down a very large program into much smaller pieces and much smaller chunks by using objects. You test each object independently. Okay, so you can see how breaking this all down is going to help you with error checking and problem solving. You can also solve one module or one object at a time. So you can either correct a piece of an object or the entire object itself. That really is the rest the end of the information for module 2. You guys did really, really good on the case study for module 1. I was very impressed reading through them. You guys did amazing on them. There was a lot of critical thinking going on in a lot of them. In most cases, I did give feedback. In some cases, I gave feedback within the PowerPoint and then reattached it for you to view if that was necessary. If there was no attachment, it just means whatever was written was sufficient. But I was really impressed with you guys and the case study. Now, things coming up, the case study for module 2 is due by Friday at noon. So that is something that you need to make sure is on your calendar because there was some little confusion with due dates. So Friday at noon. The other things that are due this week, and I know I had my Carolina U up here somewhere, is the Use It, which is the homework exercise that is individual. But you can take it as much as you want. So there's a module 1, Use It if you've not done it, and a module 2, module 2, Use It if you've not finished it. Then there's also quiz 1 and 2. Please remember, and I think everybody that's here in person has done the onboarding, but please remember onboarding must be done 24 to 48 hours prior to you wanting to take the quiz. Okay. It has to go through the system. I have to approve it as a student, and then you're able to take the quiz. If you have any issues at all whatsoever, cannot access your book, cannot access your ebook, shoot me an email immediately. Okay. I know that we are the guinea pigs with this proctoring software, and I have gone through several problems so far. But please let me know if you're having any problems with the proctoring software. I'm not going to be using the proctoring software unless it's obvious that you're cheating. We're just being the testers, okay? So I don't want anyone to really take that, you know, out of context. But again, your quizzes are open notes, open book, closed Google, open brain. I guess that's it. Is there any questions, comments, concerns?